Hi everyone, this is Kalyan Kumar this side and welcome back to Chemistry Universe. This is video number 2 of aldehydes and ketones, and in this one we are going to talk about preparation of ketones. So let's quickly get on with the video. So preparation of ketones, and a lot of things are going to be similar to aldehydes. For example, we do the oxidation of secondary alcohols instead of primary with mild oxidizing agents. We've done this in alcohols. So you have an alcohol. Again, I've taken the allyl alcohol for a particular reason, and then a normal alcohol. So if you use NBS, it's going to oxidize both. If you use the Fenton's reagent, again it's going to oxidize both. But remember, they are not oxidizing the double bond. If you use PCC, PDC, and CTP, then you're going to get again both. If you use MnO2, remember MnO2 is specific for allyl and not for a normal alcohol. With tertiary butoxy aluminum, you'll get both, but double bond is not affected. With calcium ammonium, with ceric ammonium nitrate, you can again get both. And with silver at 300 or copper at 300, you're going to get both. Now, the next one is the oxidation in the case of strong oxidizing agents, because you can do it with strong. And of course, here you don't need special distillation like you did in aldehydes. It will directly give you ketone. Ketones are very resistant toward oxidation, unless and until, of course, use extremely vigorous conditions, which we will see in the reaction of ketones. But if you use something like a PCC, remember, if you take this alcohol, now this is a secondary alcohol, it should become a ketone, but PCC is very sensitive to hindrance. So it's not going to affect the hindered OH. It's going to only do with this OH. Okay, so you will find that the top one gets oxidized with PCC, but if you were to use KMnO4, it will oxidize both. So PCC does only the unhindered one, KMnO4 does both. So if you have this, for example, if you use PCC, it's only going to oxidize the ketone, the alcohol into a ketone. But if you use KMnO4, remember KMnO4 can also oxidize the double bond. We saw it in alkenes, and it will convert them into acids. And just like aldehyde, we can do the dehydrogenation of secondary alcohols using copper at 300. It will remove one H from both carbon and O and convert that into a carbonyl compound. The next is a very interesting reaction. It's called the Oppenauer oxidation. Now, Oppenauer oxidation, named after Rupert Victor Oppenauer, is a gentle method for selectively oxidizing secondary alcohols to ketones. And this is the opposite of Mervin-Pondorf-Verley reduction. The alcohol is oxidized with aluminum isopropoxide in excess of acetone. Now, you will see this when we do the reactions of aldehyde and ketones, that you can selectively oxidize a secondary alcohol into a ketone and reduce a ketone into a secondary alcohol without affecting any other functional group. That's the beauty of this particular oxidation. Because just like you saw in KMnO4, it also oxidized the double bond. PCC didn't, but KMnO4 did. But PCC could probably even affect other types of alcohols. Okay? Whereas this one is very, very specific. It only does alcohols if it will not interact with any other functional group. The oxidation is highly selective for secondary alcohols and does not oxidize other sensitive functional groups such as amines, alkenes, etc. Though primary alcohols can be oxidized under Oppenauer oxidation, primary alcohols are seldom oxidized by this method due to competing aldol condensation of aldehyde products. You see, what happens is, why do I insist on secondary alcohol? Because it is used only for secondary alcohols. It's never used for primary alcohols, because primary alcohols, what they do is that they become aldehydes, and but the aldehyde don't stop there. They show a further reaction called aldol condensation, which we will see later on. So it is always better to do this for ketones, for secondary alcohols to ketones. So secondary alcohol reacting with acetone with the aluminum isopropoxide with isopropyl alcohol and heat. Now just try and understand this first before I show you the product. Now remember, this is acetone. The important ingredients are, you need an acetone, because what will happen is you will oxidize this and you will reduce this. Oxidation always has to be followed by reduction, right? So this is going to get reduced to alcohol, whereas this is going to get oxidized to ketone, which is what we want. We are doing the preparation of ketones. Now, the aluminium salt that you use is that of isopropyl alcohol. What is this isopropyl alcohol? Of course, I'm missing one carbon here. It will be something like this, okay? This is going to be an isopropyl alcohol. So there are two CH3s attached to a carbon, and there is this OH. So it's basically the aluminium salt of isopropyl alcohol. And the alcohol that you're using is also isopropyl alcohol. So everything is the same. So I mean, this is the salt of isopropyl alcohol. I'm using isopropyl alcohol, and I'm using the ketone of isopropyl alcohol. Because what will happen if you oxidize this? You'll get acetone, right? So this is important here. So you end up getting the secondary alcohol as the ketone and the acetone used as alcohol. Later on, you will also realize that actually this is not from this, it is from one of these. And this forms an alcohol and goes and attaches to aluminum. It's so funny. I mean, the way the reaction is written, it seems that this actually got reduced. It does get reduced. But what is happening is it doesn't get reduced directly to alcohol. It will reduce and form the aluminum salt. And one of the alkyl groups of the aluminum salt will become this alcohol. Let's see this mechanism. And it's important to know the mechanism also. So I have the secondary alcohol, right? I've got this one. Now I'm going to use this aluminum isopropoxide. Remember, this is one of the isopropyl groups, or rather isopropoxide group. And this is what happens. The bond between the O lone pair attacks the Al, and the bond Al-O bond shifts to O, and you are going to be getting something like this. And what happens to the other part? It becomes this. And what it does, it takes the H. Won't you get this one now? So which one is giving the alcohol? One of the isopropoxide group of the aluminum salt. So basically, you are going to end up getting isopropyl alcohol, which is basically this. And what will happen to this stuff? It will become this. So remember, now this O has attached itself with aluminum. Okay. Now the acetone comes. So far the acetone had no role. Now the acetone comes. It will attack the aluminum. And then you're going to get something like this. Just have a look. Take your time. Try and figure this out. What I've basically done. This is the acetone's O. It is this O. Forms a bond with aluminum. All I've done is I've just exposed the other groups of aluminum. So one of the isopropoxide groups is this, and rather two of them, and this part is this. So now what happens? So this is what happens now. The H attacks the carbon, pi bond shifts to O. This shifts here. Isn't it converting this alcohol now into a ketone? So don't you think I'm going to get something like this becoming this? I'm just showing you this again. You get the transition state. Everything is single step, concerted mechanism. And you get the ketone and the alcohol. Now the ketone is the ketone of the alcohol used, the secondary alcohol used. But the alcohol that we got, actually we got it from aluminum. Now the reverse of this is called MPV reduction, Mervin-Pondorf-Verlet. It's a reduction reaction that converts ketones to secondary alcohols by the reverse of this mechanism. And it has its mechanism the reverse of the above reaction. So that's the beauty. The next is, remember calcium and barium salt of carboxylic acid we used? Now in aldehyde we had to use one of the calcium salt as that of formic acid. Here you don't need. Take any calcium salt of any carboxylic acid, any other carboxylic acid other than formic acid. Do dry distillation, you'll get ketone. And then you can do by treating acid halide with Gilman's reagent. Now, this is again a pretty important reaction. This is Gilman's reaction, R2 Cooley. And then I have acid chloride. Basically, what the R does is attack the C part of this and remove the Cl, and you'll get ketone. Now, we don't do this with Grignard's reagent because Grignard's reagent is very reactive. It will again attack this and form tertiary alcohol. If you remember organometallics, we have done that. Grignard's reagent can also react with acid chlorides, but the product is tertiary alcohol because the ketone produced react with the excess of RMGX. So if I were to do this, it will first give the ketone, no problem. You do the hydrolysis. If you do have excess of RMGCl, it will again attack this and form tertiary alcohol. So you want to stop it at the ketone stage, make sure you use Gilman's reagent. And this shows that organocopper reagents are less reactive than Grignard's reagent towards carbonyl group of ketones, and the reaction stops at the ketone stage. Now, this low reactivity of organocopper compound is useful in the light that it does not react with the functional group with which organomagnesium and organolithium may react. Thus, the presence of some functional group like NO2, CnCO, CO2R does not interfere with the synthesis of ketones. If you remember, just check out the organometallic video. We used to have RMGX reacting with esters. In fact, two molecules of RMGX reacting with esters. Two of them reacting with RCOCl. So all of that was happening because it's a pretty strong reactive. It's more reactive than the organocopper. Organocopper is mild, so it does attack once and that's it. So and it doesn't even react with esters because esters are themselves less reactive than acid chlorides. So if you have this, and if you take R2CuLi, you take half because you're taking one of this, you'll get the ketone there. Cl replaced by R. But if you were to use the Grignard's reagent, then the problem is it is the SI form that reacts. Remember, the tautomerism of nitro is SI form. Now in the SI form, there's an acidic H. So what will RMGX do? It will take the acidic H. So instead of Gilman's reagent, dialkyl cadmium can also be used because even this is less reactive. Now, the next one is the Friedel-Crafts acylation, which we have done in EAS. We can do a similar kind of acylation of alkenes. Now, basically what happens is you have an alkene acting as a nucleophile and causes nucleophilic substitution of Cl of RCOCl to give you alpha beta unsaturated ketone. So what happens is you have this, and this is going to act as a nucleophile. So basically what it does is that, it's something like this happening. This attacks this and the Cl leaves, and you will obviously get a ketone. Of course, this becoming plus, the Cl will attach here, and then, effectively you can remove the Cl as unsaturation. And I'll show you the mechanism soon. Of course, you use a Lewis acid like BF3. So what happens is that you have acid chloride with BF3, and the lone pair attaches to boron, and the Cl leaves, and you get an acylamine. And you know that alkene is a much better nucleophile than even benzene. So this goes here, attacks the carbon, and you get this. And remember, the Cl will come back and attack this, and and this takes the H, and you get alpha beta unsaturated ketone. So that is how this reaction occurs. And the reason Cl doesn't attach to the carbon and takes the H is because this shows resonance, and therefore it's a more stable product. Now, let me ask you this question, and hold the video, pause the video till you get the answer. I want you to think of a reagent that can reduce my ketone into the alcohol as well as double bond into an alkane. Think of any reagent. Okay. So which one do you think will give you this? H2PT. H2PT can reduce ketone into alcohol and carbon double bond carbon to alkane. Now, suppose I only want the ketone to be reduced. I only want the ketone to be reduced. I don't want the double bond to be reduced. Use MPV. Use MPV reduction. You can even use LAH. But I want, now comes the difficult part. I only want the carbon double bond to be reduced, not the ketone part. Pause the video, think. Here is the answer. You have to use a new reagent that you haven't done so far. And that is called this. This is called Wilkinson's catalyst. So it's called chlorotris triphenyl phosphine rhodium 1. And this is called the Wilkinson's catalyst. It is used for selective hydrogenation of alkenes and alkynes without affecting other functional groups like carbonyl, CN, NO2, aryl, CO2R, etc. Now you can also get ketones by heating dicarboxylic acids. Now when the calcium and barium or thorium salts of carboxylic acids are distilled, cyclic ketones are produced. Now try and get this. Suppose I have a molecule like this. Try and understand what this molecule is. It's basically calcium salt of a dicarboxylic acid. Imagine you had a dicarboxylic acid like this. Okay? And you formed a calcium salt. So it has got two COH. It doesn't need two molecules. In one itself, it can form a calcium salt. Okay? Now, if you do heating of this, you'll get a variety of products depending on the value of N. You can get a cyclic, what is this? Anhydride. Okay? You get a cyclic anhydride. And you can get a cyclic ketone. You can even get an acid. And you can even get an alkane. It all depends on the value of N. Now, if you wanted to get anhydride, now in this anhydride, you got one as one, since it's going to be a cyclic one is carbon, 2 is oxygen, third is again carbon. And you know that only 5 and 6 membered ring can easily form, right? So what should be the value of N to give you this? To get a 5 membered ring, it will be 2. To get a 6 membered ring, it will be 3. So when N is 2 or 3, you get this. Now let's look at the cyclic ketone. One of the components is this carbon. So what should N be? Can you think? Pause the video. Think. Well, since one of them is carbon, N needs to be 4 or 5. So what should be N to give you a simple carboxylic acid? Well, it needs to be 1. We have done this in the case of alkanes. You know, one COH attached to carbon and another COH. This will act as beta keto for this. So mere heating will remove one, not the other. But if you want to remove both, the N better be more than 5. So that. Now you can again get the heated MNO if you remember. Something similar we did in aldehydes. So vapors of monocarboxylic acid other than formic are passed through manganese oxide at 300 and ketone are formed. So just like aldehyde, you got ketone here. Ozonolysis, we have done this. Only thing is make sure there are no H here. And we have done the Kucherov reaction, remember? Alkynes. You have HgSO4, H2SO4. We have discussed this in alkynes. And we've also done Oxymercuration-Demercuration of alkynes to give you ketones. Generally, Oxymercuration-Demercuration of alkenes gives you alcohol. With alkynes, it gives you ketones. And it is going to be, a Markovnikov addition. You can even do Hydroboration-Oxidation, but make sure that none of the carbons are terminal carbons. Otherwise, you'll get an aldehyde. You can do hydrolysis of Gem Dihalides. This we have already done. The only thing is, we use Br2 instead of Cl2 because Cl2 will end up getting more on the terminal carbon than on the middle carbon. If you want to know why, go and check out alkanes, halogenation reaction of alkanes. You'll understand. Bromine is more selective and chlorine is more reactive. So bromine comes on the middle carbon and you have OH minus and you get this. You can even use acetoacetic ester. Basically, this is acetoacetic ester, and what happens is, because of the two C double bond O's, this H becomes quite acidic. So what happens here is that when you use a strong base like ethoxide, you get a carbon ion, the H will easily be lost. Then you treat it with Rx, this will act as a nucleophile on R, and X will leave and you'll get this. Do the hydrolysis of the ester, acid, hydrolysis, you'll get acid. Remember, it's a beta keto acid. All you got to do, heat it and you get a ketone. And then we have also done HIO4 oxidation, periodic oxidation in alcohols. We have done Pinacole-Pinacolone reaction. We got a ketone, remember? You can even use Grignard's reagent on nitriles. And RMGX with RCN. R minus is a nucleophile, attacks the carbon, and you'll get, in this case, you'll get an imine first. And that imine will become a ketone. And we have already done beta keto acid so many times now. And we have done Fries rearrangement in phenols. And with that, we end the preparation of ketones. So you saw that many of the reactions were repetitions. Make sure that when you watch this video, you watch them in sequence. If you have missed the previous lesson, you won't be able to understand this lesson. The way I've structured this, especially organic chemistry, the way it is structured in such a way that you have to look at the previous video, make sure you understand all the previous videos. And even if you don't remember everything, at least they should be similar to you. And then just go back and go to your notes and check out which part I'm talking about, and then come back and you'll be able to understand these things better. And as you see, I was going a little faster, mainly because most of the reactions we've already done. And this is what will happen in organic chemistry. As we go from one lesson to the other, most of the reactions will keep getting done and there'll be a lot of repetitions. And in these cases, I don't want to show the reaction once again and waste your time. So what you need to do is just go out and check out the previous lesson wherever this particular reaction was done. I'll mention that, of course, while I'm talking about that particular reaction. With that out of the way, this is Kalyan Kumar signing off. Have a great and productive day, and thank you for watching this.